Okay, thank you. Thank you very much for the invitation. So today I'm going to talk about precision auto-tuning and control of accuracy in numerical simulations, in particular using the CADNA tool. Okay, as you know, when you do numerical simulations, you usually use floating point arithmetic. And in a floating point number, you have its sign, its exponent, and its mantissa. And in the table here, you have various floating point formats. For each format, we have the number of bits in the mantissa, in the exponent, the consequent range, and U, which is a unit round of error, which is the best possible accuracy. And in software, you usually already have single precision and double precision, which are usually used. But you have also, for instance, half precision, which is increasingly supported by hardware. For instance, in recent GPUs, also on recent ARM CPUs. And if you decrease the precision, if you decrease your format length, you may decrease your execution time. In particular, if you use SIMD vectorization, you will also decrease the volume of results exchange if you do a parallel execution of your code, and you will improve energy efficiency. Actually, the energy consumption is proportional to p squared, where p is a number of bits in the mantissa. So if you go from double to single precision, you will consume 5 times less energy. And if you go from single to half precision, you will consume between 5 to 9 times less energy, depending on your format. But of course, computed results may be invalid because of rounding errors. And so in this talk, we aim at answering 2 questions. First, how to control the validity of mixed precision floating point results, and then how to determine automatically the suitable format for each variable. There are several approaches for rounding error analysis. You have, for instance, interval arithmetic that consists in computing with intervals that always contain the exact result. And this approach provides guaranteed bounds for each computed result, but the error may be overestimated. If you use interval arithmetic in a naive way in a large code, you may obtain at the end minus infinity, plus infinity. With this approach, specific algorithms have been proposed that tend to contract the intervals. And you have also the static analysis, which is a rigorous analysis that requires no execution and that takes into account all possible input values. But unfortunately, it's an approach which is not very well suited to large programs. And you have the probabilistic approach that will estimate the number of correct digits in any computed result, whatever the algorithm. And this approach requires no algorithm modification and can be used in HPC programs. For each approach, I mention some tools, and for each of them, I give the oldest reference. Okay, so today I'm going to talk about a probabilistic approach, which is named discrete stochastic arithmetic. So with this approach, each arithmetic operation is executed 3 times with a random rounding mode. So it means each result is rounded up or down with the same probability. And so instead of having for each operation 1 result, we get 3 results that can be compared. And the number of correct digits in the results can be estimated using student's test with the confidence level, which is chosen to be 95%. And with this approach, all the operations, all the arithmetic operations are executed in a synchronous way. So that means each operation is executed before going to the next one. And that enables us to detect numerical instabilities. So for instance, unstable tests, where the difference between the operands is numerical noise. And it also enables us to optimize stopping criteria. So it means we will avoid useless iterations that would only bring numerical noise to the solution. And this approach is implemented in the CADNA library. CADNA implements stochastic arithmetic and can be used in C, C++, or Fortran codes. This library provides stochastic types. A stochastic type consists in 3 floating point variables because of the 3 executions, and 1 integer to store the number of correct digits. And so the library provides stochastic types of various precisions that can be mixed together or that can be mixed also with classic numerical floating point types. And all operators and mathematical functions are overloaded for the stochastic types. And so using CADNA in a code actually requires a few modifications in user programs, mainly modifications in type declarations. And CADNA can be used with parallel codes using MPI and or OpenMP. Also, it can be used on GPU codes written in CUDA and on vectorized codes. And in one CADNA execution, we can get the accuracy of any result and also a complete list of numerical instabilities. And so there are several floating stochastic types in half precision, single, double, and quad. And I give a few more information about half precision in CADNA. With CADNA, we can control FP16 half precision computation, either with emulated half precision, thanks to a library, or we can control native half precision computation carried out, for instance, on NVIDIA GPUs or on some ARM processors. And as a remark, we could do successful tests with CADNA on the Fugaku supercomputer using ARM processors. And CADNA also enables us to control quad precision computation. And in this case, we actually use the quad precision types, which are provided by classic compilers such as GCC and ICC. So our quad precision stochastic types is based on these types provided by the compilers in software. So, of course, CADNA has a cost, which is 4 in memory and about 10 in execution time. This overhead of 10 is an approximation. It can be more, depending on the detection instability level, and also depending on the fact that the initial code may be very well optimized for classic floating point arithmetic. And over the years, we have spent much effort to try to reduce the cost of CADNA. So one trick we used is not performing explicit change of the rounding mode, but implicit change to the rounding mode, thanks to arithmetic properties, which are given here. And we also develop another library, which is called SAM, which also implements stochastic arithmetic, but this time in arbitrary precision. So with SAM, we provide stochastic types, which are based on the MPFR library. And again, we rely on operator overloading. So again, SAM requires a few modifications in user C or C++ programs. And actually, there are two versions of SAM. The first one, which is a uniform precision version, and the other one, more recent, which is a mixed precision version that enables us to control operations that mix different mantissa lengths. So, for instance, you can control rounding errors that would occur in operations that mix variables A, B, and C, each one having its own mantissa length. And that is particularly interesting for accuracy estimation on FPGA, where each variable can have its own mantissa length, and this length is crucial for performance. I give you now a quick example of computation. So first without, then with CADNA. So we want to compute this expression P for two couples, X and Y. So here you have the classic code. And so this code is run in double precision with rounding to nearest, and we obtain these results. But here you have no information on the numerical quality of the results. So we decide to use CADNA in the code. So we declare the use of CADNA. Then here we use an initialization function. -1 here means that we want to detect any kind of numerical instability. CADNA end here is a function that will provide us the instability report at the end of the execution. And we change the types. So we go from classic double precision to the stochastic double precision. And here you have the results. So you can see that all the instability flags are set to on, activated. And with the first couple, you have a symbol that means that we get no correct digits. And with the other couple, we get 15 correct digits, which is a maximum accuracy in double precision. And you have also the instability report. So here we have performed to compute P1 two cancellations. That means we have subtracted two close results affected by rounding errors. So here you can see that with a simple code, you can lose all the accuracy. And we have two completely different answers with the same computation depending on the data. And so now I'm going to show you a more real-life example. CADNA has been used to explain reproducibility failures in a wave propagation code. So here we want to solve the acoustic wave equation. So this equation is solved for oil exploration. And in this equation, U is the acoustic pressure, C is the wave velocity, and T is the time. And this equation is solved using a classic finite difference scheme of order 2 in time and 8 in space. And actually, there are two implementations of the finite difference scheme. So these implementations are mathematically equivalent. So mathematically, we do the same computations, but the order of the computations is different from one implementation to the other. With the first scheme to compute a result, we use the nearest neighbors first. And with the other implementation, we use all the points in dimension 1, then 2, then 3. And actually, reproducibility problems have been observed. The results depend on the implementation of the finite difference scheme and also the compiler, the architectures which are used. And the various tests had been carried out on different CPUs, different GPUs. And in single precision, if we use a space step of length 64 and 1000 time iterations, which are reasonable parameters, any two results which should be equal have actually between 0 to 7 common digits. And the average number of common digits is about 4. So we see here some results in the space domain. We choose 3 points in the space domain, and we compare the results for the different schemes, and also for different CPUs, GPUs, different compilers, different environments. And here for each point, you have in bold the number of common digits. So you can see that this number of common digits actually depend on the point which is considered in the domain. Okay, so as a recall, we can have between 0 to 7 common digits between these points that should be equal. And so the question is how to estimate the impact of rounding errors. And so we run the code with CADNA on CPU and on GPU. And with both implementations of the finite difference scheme, the number of exact digits varies from 0 to 7. 7 is the maximum because we are in single precision. And the mean value of the number of correct digits is about 4 on CPU and about 3.5 on GPU. And these results are consistent with our previous observations. And CADNA has also detected numerical instabilities, more than 200,000 cancellations. So cancellations are subtraction of close values affected by rounding errors, as I said previously. And that is not surprising because here we use a finite difference scheme. And so with this scheme, we very often subtract close values. Okay, so here we consider again our 3 points. And you have the results which obtain without CADNA on CPU, GPU, with CADNA on CPU, GPU. So here with CADNA, we only display the correct digits, the digits which are not affected by rounding errors. And we also show the reference result, which is a CADNA result obtained in double precision. And you can see that the number of correct digits depends on the point and can be slightly different also on CPU and GPU. But despite differences in the estimated accuracy, the same trend is observed on CPU and GPU. So it will be better with the graph. Here on this graph, you have what happens on CPU. You have on the x-axis the absolute values of the result, and on the y-axis the accuracy, the number of correct digits. And you can see that for results which have high absolute values, these results are actually accurate, and the highest errors actually impact negligible results. And here you have the associated graph on GPU. So you don't have strictly the same results, but you can see the same trend. Highest results are actually accurate, and highest errors impact negligible results. So this is here a good ending story. We have another example, which is a numerical simulation of a shallow water simulation on GPU. So here we simulate the evolution of water heights and velocities. And we have a GPU code, a CUDA code in double precision. And we are interested on the eddy evolution. And we compute 20 time steps, which correspond to 12 hours in real life on a square grid. And on the left here, you have the results obtained at the end of the simulation. So here we have the square of the work velocity. And on the right, the number of correct digits estimated by CADNA. And you can see that at the eddy center, there's a great accuracy loss, which is due to cancellations. And the point at the very center has lost 9 digits. So it means that if we perform this simulation in single precision, we would have no correct digits for the points at the center. So the simulation here must be carried out in double precision. And fortunately, velocity values are close to 0 at the eddy center. So actually, these errors have negligible impact on the output, and the overall accuracy remains satisfactory here. There are tools related to CADNA. You have what we call a CADNaizer, which automatically transforms C++ codes to be used with CADNA. So the transformation that I have shown to you previously can be done in an automatic way. We also have CADTrace, which is a tool that will identify which instructions are responsible for numerical instabilities. So here you have the results obtained with a very short Fortran example code. And there are also other tools, other numerical validation tools, which are based on result perturbation. You have, for instance, Verificarlo, which is based on LLVM. You have Verrou, which is based on Valgrind, and it's particularly interesting because it requires no source code modification. And these tools have an asynchronous approach. So with these tools, you perform one complete run to get one perturbed result. So it means you must carry out several executions for rounding error analysis. And also, if you want to point out instabilities, such as unstable tests. And for the moment, these tools provide no support for GPU codes. And a cost comparison had been performed using arithmetic benchmarks. And for the comparison to be fair, 3 samples had been computed with each tool. And here you have the overhead obtained with respect to a classic execution, a classic floating point execution. And so what happens if you use a numerical validation tool and if you observe that your results accuracy is not satisfactory? You can increase the precision, you can use higher precision until arbitrary precision if necessary. And if you do that, you must still be sure that your results are valid. So you must not forget numerical validation. You can use also compensated algorithms. They can be used, for instance, for the sum, dot product, and they will provide results which are almost as accurate as with twice the working precision at the price of extra operations. And you also have libraries that will provide accurate and reducible BLAS, so basic linear algebra kernels. And I give here a few references. So several of these libraries have been developed in France, in the US, in Japan also. And then if you are happy with your results, the next question is, can we use reduced or mixed precision to improve performance and energy efficiency? There are several mixed precision linear algebra algorithms that have been recently design proposed. This is a very active research axis. And you have, for instance, a survey of Hayam and Mary that will detail the results obtained for various problems. And you have also precision auto-tuning tools. So here you have a few references for static tools, which unfortunately are not well suited to large-scale programs. And on the other side, you also have dynamic tools, which intend to deal with large codes. So you can see that it's an active research axis. There have been several tools proposed over the years, and some are linked together. For instance, parsimonies and blame analysis are linked together. You also have Flotsmith, which is actually a combination of two tools, craft and adapt. And there are tools also which are dedicated to GPUs, which pay particular attention to avoiding casts. But all these tools rely on comparisons with the highest precision results. And that can be dangerous. You have here an expression which is computed first in single precision. And you get a result which is about 10 to minus 29. And then you decide to perform your computation with double precision. And you get a completely different result. You get about 1. So you decide to see what happens in quad precision. And you have a result which is very consistent with what you had obtained in double precision. But actually, the exact result is negative. So here, even with quad precision, you could not get the sign of the exact result. And so you actually need numerical validation to perform precision auto-tuning. So we have proposed the PROMISE tool that provides a mixed precision code. So that can mean, for instance, half, single, and double precision, taking into account a required accuracy on the results. And PROMISE uses CADNA to validate each type configuration. And PROMISE relies on the delta debug algorithm to search for a valid type configuration with a mean complexity of n log n for n variables. So it's not an exhaustive search, but it will provide a mixed precision configuration with a reasonable complexity. And now I'm going to briefly show you what happens with the delta debug algorithm if you have two types. We assume that you have a code that provides satisfactory results with the highest precision. And if you run it with the lowest precision, you don't get satisfactory results. So we split the set of variables. And imagine here that we get configurations which are not satisfactory. Then we split again. And here you have on the left a configuration which is successful. And we will go on with this branch. And the 3 configurations on the right will not be tested because it's not an exhaustive search. And so you will go on with the branch on the left. And here you have a configuration which has already been tested previously, so it's not tested again. And you get a configuration which is successful, and you will go on with this branch and so on. Okay. And if you want to use PROMISE with 3 types, 3 precisions, so for instance, double, single, and half precision, you will have to use the delta debug algorithm twice. So first, to determine from the double precision variables which one can be relaxed to single precision. And then you use your delta debug algorithm again from your single precision variables to know which variables can be relaxed to half precision. And so we have a few examples. For instance, a conjugate gradient code. So we have used the sequential version of a conjugate gradient code from the NAS parallel benchmark suite. And so the code here solves a linear system with a matrix of size 7,000. And we look what happened after 15 iterations. So in this table, you have the number of required digits on the solution vector, the number of executions which are performed by Promise, the configuration which is provided by Promise, so the number of variables in half, single, and double precision, and the time taken by the tool. So in this time, you have the time taken by the compilations, the executions, and the time spent also in internal Promise routines. And you can see that if a few digits are required on the solution, for instance, you don't need double precision. But if you ask from 8 digits on your solution, then you start to require double precision. Promise has also been used on Mikado, which is a code developed by EDF, which is a French energy supplier. Mikado is a code that simulates nuclear cores. It's a code that solves a transport equation. And you have, again, in this table, the number of required digits on the solution, the number of variables in single, double precision, and the speed up and the memory gain with respect to the double precision version of the code. And you can see that the speed up is up to about 1.3 and the memory gain 1.6. But actually, these values have been obtained with the single precision version of the code. And the mixed precision approach remains successful. With the mixed precision approach, we have a speed up of 1.2 and a memory gain of about 1.4. Now I'm going to briefly present works in progress. We work now on precision auto-tuning of neural networks. So here we have an example of a classification network for CFAR. So in this network, we have 5 layers, including convolution layers. And we have to set a bit more than 100 types. And in this graph, you have on the x-axis number of digits, the number of required digits in the solution. And you have the number of variables of each type. And so you can see here that with this classification network, you have always 22 variables that can remain in half precision, whatever the required accuracy. And this is something that has been observed for CFAR, also for MNIST. So we have tested a few classification networks, and we always have half precision variables that remains. And you have in orange here the time taken by the tool, which is very dependent on the required accuracy. So if you require a high accuracy, you will perform more executions of the code. If you are interested, you have the reference to the associated article here. And some of you, I guess, are very interesting also in the fact that we also work on the numerical simulation of C++ codes, which are related to Agatha. So this is a work in progress. So some of you know certainly very well Agatha, which is a European gamma ray spectrometer. And we collaborate with IJC Lab in Orsay to study the impact of precision, half, single, and double on the accuracy. and also to produce a valid mixed precision version of the code. So before my speech, CHEP has been mentioned. So the current results will be presented in the CHEP conference in May. And so as a conclusion, if you want to optimize precision, you have several numerical validation tools, such as CADNA. You have also precision auto-tuning tools, such as Promise, and you have also mixed precision algorithms that have been designed. And as a perspective, we would like to extend CADNA and Promise to other formats, such as bfloat 16. We would like to extend Promise to GPUs. So CADNA version exists for GPUs, but not Promise for the moment. We also would like to propose floating point auto-tuning in arbitrary precision. So for the moment, you have seen that you can use Promise in half, single, double, maybe soon in quad also, but it would be interesting to go to the arbitrary precision. One of the targets here is, of course, FPGAs, but that brings algorithmic problems because the number of possibilities will be very huge with arbitrary precision. We would like also to combine mixed precision algorithms and floating point auto-tuning. So the aim here would be to improve the performance of precision auto-tuning by automatically use mixed precision algorithms when they exist. So we would automatically recognize linear algebra kernels, and if they exist, use the associated mixed precision algorithm. Okay, so here you have a few references, a few papers. You have also the link to the 3 tools. Here you have a list of people who contributed to CADNA, SAM, and also Promise. And of course, I would like to thank them very much, and also to thank you for your attention. And I will be very pleased to answer your questions.
Thank you very much. Thank you very much, Fabienne. Very interesting talk. Any questions? Okay, I see the first hands already rising. Andrea, you are first.
Yeah. Thanks a lot, Fabienne. This was extremely interesting. Actually, I have 2 questions. The first one is easy, maybe. On slide 23, you talk about this cut trace. So I was just wondering if this is what, I mean, the point is that we have a Monte Carlo code which has numerical issues, and we don't know where it is. So I was just wondering, is this cut trace a tool that you could just use to say, to at least get the first feeling where the problem is? And then the second question, maybe I just ask it immediately, which is about this mixed precision. It's very interesting. I was just wondering, in general, what's your take on that? I mean, is it easy? Is it useful? Because we developed some mixed precision algorithms, but it was a bit complicated, especially because when you move from the variables, you have to copy them from float to double and vice versa, and then you change the SIMD. So it can be a bit complicated. So I'm a bit surprised that you have something that seems to do it automatically, and how effective is that?
Mm-hmm. Okay, so first question about cat trace. What you could do, yes, is use CADNA in your code. Then you will end up with a list of instabilities. And what the cat trace tool does is telling you at which line in your code each instability occur. Because if you run a real life code, you may end up with 200,000 unstable tests, 100,000 unstable multiplications, and so on. And if you, so you have CADNA facilities to be able to deconnect or to activate or deactivate the search for, well, the instability detection, and you may have answers like that. But this tool will give you quickly a list of the lines in your code where the instabilities occur. So it will enable you to save time. And then you have to go to these lines to see exactly what happens, where the problem is. Do I have to increase the precision, increase the format? Do I have to write again my algorithm? This is what the CATRAS tool will provide. But yes, I think it can be interesting if you suspect something.
Thanks a lot. Yeah, we'll definitely use that. Thanks a lot. Yes.
Okay, and I will be happy to help if you need, of course. And the other question was about Promise, and so okay. So Promise will give you an answer which is not the optimal configuration because it's not an exhaustive search. But it will help you to save time. Instead of modifying by hand and trying to look what variables can go to single precision and try to compare with a validated reference result each time, and that can be very time consuming. It can give you a configuration, and then you can see if there's a single precision variable which is alone among many double precision one, maybe it's not interesting. If you have a cluster of single precision variables, then maybe you can use SIMD vectorization there to improve your runtime. And so, yes, it will provide you a configuration, and then you will be able to know with this, well, to test if this configuration, with this configuration, it's okay. And then if you have to modify again some of the some variables and go from single to double precision for some of them, you still know that your answer, your results accuracy will be valid. And then you do what you want with the optimization, vectorization, and so on.
Thanks a lot. Okay, so it's a bit more like a profiling tool than really a production tool. I mean, I understand. I think it's very interesting what you said. Very, very nice. Thanks a lot again for the talk.
Yes, I would like to say a few more words. Actually, there's a question. Can we are not obliged to use CADNA in production, of course. CADNA will enable you for representative data sets, to tell you if your code is valid or not. But then when you have tested sufficient data sets, you can go into production without CADNA. So it can be used as pre-processing or during your development steps. And then when you want to get the full performance from your code, you don't necessarily use CADNA.
Okay.
Thanks
Maybe
again.
Just a follow-up question. CADTrace would also work with C++ CUDA codes, or
yes, well, it has been tested. It's based on GDB. We have tested it on Fortran and C++ on CPU, not on GPU for the moment. So I'm not sure about GPU because it relies on GDB, and so we have to test. For the moment, I don't guarantee.
Okay, thanks.
Well, it depends on how it relies on GDB, because the debugging tools are pretty similar.
Yes. Okay. Next, Charles, please.
Right, thanks. So I had a question concerning the power utilization that you quoted for. You said it went with a square of the number of bit reduction. Have you actually tested this in practice on various types of machines to see if that actually, I mean, how that is represented in real life situations?
You mean this p-square here? Okay, so I guess you were interested by that. It's from literature here. So I could give you the reference, but there is one article, and I think some of them who have established this rule, saying that the energy consumption is proportional to p-square. So it's not something that I have measured myself. It's taken from literature, and I can look for the reference I have used if you want.
All right, thanks. I would love to see that.
Okay.
Yeah, actually, I would be also interested in this. Yes.
Okay. Thanks.
Thank you.
Please write me an email for me to have your address. Okay.
Will do. Okay. Michael.
Yeah, Fabienne, thank you. This was a wonderful talk, and actually that's a very nice development. And
Yes.
I'm going also in the direction of GPU accelerators and CUDA C++, and you basically have answered my question already, since there have not been extensive tests, but we of course know if you change the precision in multi-thread CUDA implementation, of course also the utilization of the GPU usually changes drastically, which is usually very beneficial if you go to lower precision. However, there are certain algorithms that you do in parallel that if you do more computation in a serial manner or in a parallel manner, they also change in the precision of their output, especially if you look at architectures like GPUs, where you cannot guarantee a deterministic execution of parallel threads. So I was wondering, does this add to the complexity of analyzing such a code in the end, in terms of the sheer parameter space you have to make sure is well covered?
Okay, so usually when you have a sequential execution and then you go to a parallel execution, and if you get different results, it's because the order of the computations may be different.
Exactly.
And usually CADNA tells you, for instance, there are 5 correct digits, and in most cases, you have 5 correct digits in sequential and 5 correct digits in parallel, whatever the environment. So what CADNA will tell you is that whatever the order of the computation, you get 5 correct digits. And so you must not be stressed by the fact that in double precision, for instance, the last 9 digits are different from one execution to the other, because actually it's numerical noise in any case. And CADNA, yes, will help to explain reproducibility failures. And okay, and if you have differences, actually you get different rounding errors. And it's useless to try to always have the same result as in sequential, for instance, because it's not better than in parallel. And what CADNA will give you is the number of digits you should obtain, whatever the order.
Okay. Thank you very much. And just one comment, and I will put it briefly on the chat. There was a talk by one of our students yesterday at the CADNA Day, where they presented a library that allows you to replace C++ standard data types with different memory layouts, and this also allows you to provide arbitrary precision in settings just by changing a few lines and do mixed precision. Maybe this is helpful for implementing some stuff, especially for arbitrary precision in CADNA. I'm not sure if it's of help, but I just posted the link. Maybe you can have a look.
Yes, thank you. Actually, if your code is designed, for instance, with templates and so on, and if it is easy to change from one type to another, it will be very good for your code to be used with CADNA, because you just change from classic types to stochastic types. And if you want to validate arbitrary precision computation, so as I said, we have also a library which is called SAM for that. So it's still possible also, with only a few modifications in your types.
Okay, thank you very much. That sounds amazing. Thank you.
Attila, you have another question?
Yeah, I have some very technical, let's say one question, but I've been looking at the source code of many of these things during the presentation, and I started wondering, right now, when I looked at the web page, I was a bit unsure exactly which version of the code I should be downloading, how I would need to use that code exactly. So, and I was, one of my biggest worries when looking at this was that there is no code repository that one can look at, just downloadable tar files. So if somebody would, for instance, like to contribute, is that possible? Right now, when I look at this, I would be a little bit scared of making, let's say, Atlas code dependent on this project, because I'm not exactly sure how much development is there or how much future there is, because, it's a bunch of tar files.
Okay.
So I will try to answer your question. I'm not sure you will tell me if I did answer correctly. So one of your question, I guess, is how to contribute and how we work. So actually we have in the lab SVN, and we have code generators for CADNA that is not included in the distribution, where we have patterns, because we want to perform, for instance, addition between stochastic numbers in single precision, double precision, and also classic types, and also addition of stochastic numbers with floating point times, integers, and so on. So you have many possibilities, and so the source that you can get on the site are generated because we have common patterns, and so this is not included in the distribution. But if you are interested to contribute, I can give you access to the development of the code, and that is possible. About the various versions, okay, so we have at a time we had 2 versions of CADNA, one for the Fortran codes and one for the C++ codes. And so it means we had a library completely developed in Fortran and one completely developed in C. And it was very hard to maintain both because C++ version was evolving very quickly. And then we had to do it in the Fortran version. So then we decided to use a binding. And so from your Fortran code, actually you can call the C++ version of CADNA. That is very convenient for us for development, but the performances are not so good as using the completely full Fortran version. So for the moment, we give access to everything. So the full Fortran version, the binding, and so on. One advice would be to go to the latest versions where that have the latest modifications. And maybe I have missed some points in your question. Tell me.
No, that's so one of the things that you mentioned, I actually took very positively since you mentioned code generation, because as I was looking at the code, I got worried that you would have written all of this by hand. It's actually good to hear that much of this was generated.
It's based on M4 for code generation.
Okay. Okay. Yeah. Thanks.
Okay. Thank you. Any more questions to Fabienne before we switch talks? I don't see any hands up. Okay, so thank you very much again, Fabienne.
Thank you very much, and please, to all of you, feel free to contact me later for any question, or if you need help in the use of CADNA.
Thank you. Thanks
Thank
a lot.
you very much. Thanks.
Thanks. Okay, so let's move to the second talk of today. Michael, you want to share your slides yourself? Yeah. Okay, so the second talk is about for the case for AI-augmented facilities, and given by Michael Bussmann from CASUS. Michael, floor is yours. You're muted. You're muted.
See, my kids just arrived. That's why I was muted. So thank you very much for the invitation to present here. I'm going to present a bit lessons learned and also current state of AI use at large-scale research facilities, and some of the thoughts that have come out of a very recent Dagstuhl seminar that we did together with colleagues from Livermore, CERN, DAISY, and other facilities, to think how far AI is already implemented at facilities, and you probably know that for your facilities much better than I do, but also to have a little bit of an outlook where this could be going. So to give you a bit of a stage where this is coming from, one of my responsibilities is to define the digitalization strategy of the Helmholtz research field Matter, which is one of 6 Helmholtz research fields. And part of this is towards to go towards really automated access to facilities and optimization of research facilities. This means we also have a dedicated 7-year program on that with resources and FTAs. It's been in the making since 2015 and started in 2020. That does not just encompass this strategy, but also one on computing, on data management, and so on. So my daughter is here. You might hear her. And so this is not happening alone in Helmholtz. There is, and not just in the research field Matter, there's a lot of crosstalk across the different research fields within Matter. So for example, for energy or environmental sciences, also with national structures like the NFDI, which takes care of research data, but also with specific actions towards Sophie, bitte geh mal raus jetzt. Towards Matter and the universe applications, but also, of course, towards European strategies that cross boundaries, for example, in particle physics, photon science, neutron science, but also HPC and so on. So one of the specific examples that I want to share with you today is the use of facilities like the European XFEL, and here especially the Helmholtz International Beamline for extreme fields. I'm sorry, I just have to take care of her. So here I am. And the Helmholtz International Beamline for Extreme Fields is a high-power laser lab located next at the European XFEL, which is a large-scale X-ray laser. And this facility looks at different states of matter like you find them in astrophysical scenarios, for example, in the center of gas planets like Jupiter. But it also helps to study things like fusion experiments, where you look at instabilities that are happening at different time and length scales, and also at different temperatures and densities of plasmas. And you can really get atomistic resolution both in time and space. And finally, one thing that is very close to what I'm doing is to also study new types of particle accelerators called plasma accelerators. Here's a plasma accelerator for ions based on a simple metal foil irradiated by a laser. And you can also study these plasma accelerators at the same time and length scales and really understand on an atomistic scale how they can be optimized for applications such as radiation therapy in cancer. What you see here is one of those simulations that we use to study those systems. This is exactly one of those foil simulations, and it's running on the top 10 supercomputers right now in the world. Here's a rather old simulation already by now on Summit. We are also sitting on the European or pre-exascale systems and using them as well. And just to give you an idea what these kind of simulations mean. So this is running on more than 27,000 GPUs. This is actually what you would see live. We can go to 20 frames per second visualizations, and the data stream here is 20 petabyte per minute, which is roughly 3 times the internet traffic of the US. And the simulation itself uses sustainably 8 megawatts of power. So this is huge. This is huge in every respect, in terms of compute, in terms of data, and in terms of energy. And it's surely not, although it's fully open source, a tool easily to be used by everybody on that scale. We are limited in scale by the access to these kinds of machines. And this has been going on for a long time. So this has really been going on since 2010 when we first did that code. And we are now happy that it actually runs on CPUs, GPUs, FPGAs, and so on since 2016, using our own Alpaca suite for parallel acceleration that is performance portable across different architectures. So to give you an idea what we actually do at the Helmholtz International Beamline for Extreme Fields using the European XFEL is that we use a high power laser to generate very exotic states of matter with strong fields, high temperatures, high densities, so solid density at very high temperatures, several keV or even MeV. And we study this with the European XFEL as a tool and using simple synchrotron scattering, for example. So here you see small angle X-ray scattering images. These are for educational purposes, virtual ones. So we created them from the simulations you see up there. And you see that tiny changes, for example, in the plasma instabilities happening at the front side of the target, where you see this little red part here, also intensified here as a surface instability compared to other instabilities. You see strong changes in the signal. However, the signal from a scattering experiment is never fully invertible, so it's a non-convex inversion problem. You're not directly getting what you see up there in the simulation just by inverting the scattering signal. So this usually means that for a complex system that, by the way, changes on atomistic time scale, you really have to look at the full radiation transport of the scattering photons while the simulation is running. So you're not only putting all the particles in there, but you're also putting photons in there. And all the photons also have a phase. So you have to do huge and highly complicated sums over the different phases of the photons that scatter with the matter in the interaction. And this means they have to be highly accurate in order to later then really get create a scattering image due to interference of these photons. So this is what we see here. This is a simple slit in a real plasma simulation, a double slit, and from the photons we are spawning, we really see the usual also analytically available scattering pattern from single photon scattering at the double slit. So this is now really doable. You have this kind of photon transport within simulation, but it's hugely costly in terms of computation and memory and everything. At the same time, you also bring in all atomistic information. So atoms usually are not that simple. They can have quite complicated atomistic inner structure, and to account for this, all the atoms in the simulation can also have inner states. So again, you add to the data and the computations you have to do to have your reduced order atomistic models when scattering. So you can really do inelastic scattering with atoms by exciting atoms and de-exciting atomic states and changing them. So this is really important to get the physics right. So the same holds unfortunately true, and you can imagine with the with the data produced in the experiments. So we have at the European CAF few 10,000 shots per second are in principle available with huge high resolution detectors like the Egypt detector, providing high frequency large-scale images for analysis. So in total, we again, like everybody else, are facing the problem that both simulations and experiments produce high-rate data. And to really understand the experiments, we should have the most recent simulation data available. So we actually have to really bring together online computing of complex systems together with online analysis of complex data that we get from the experiments, because usually the beam times are about a week and they just have to work. And they are very costly. So we bring all of these together and really look at intelligence to somehow make this possible, because I cannot always access Summit while the experiment is running. So I cannot always access a high performance supercomputer system at the same time the experiment is running, although I would love to do that. In order to really facilitate this, we first have to make optimum use of the hardware, and I already mentioned it. We have several tools to do this in order to really be performance portable across different architectures, because depending on when and where we want to run the simulation, we will be facing different hardware architectures, and we have to always use the same code in order to get reliable results, and also to actually maintain the code across different platforms. So this is why we use the Alpaca solution that allows for a single source C++ code to run on CPUs, GPUs, and FPGAs, and it's also used by the CMS collaboration from the Patatrack team here, for example, at CERN, but also in other projects, for example, in photon science. On the other hand, we really have to take care of high performance IO. You already saw the 20 petabytes per minute. You cannot store this on disk. We are reaching, even on the largest supercomputers, pretty much and pretty quickly the IO gap. And of course, we start with online analysis and really streaming data analytics, meaning that we on the fly stream data from simulation and experiment through the network to further analysis routines to really reduce the data as quickly as possible and to get meaningful output there. And again, here AI will in the future play a critical role to do that. So how do we get there? So we start with the full digital twin of a planned experiment on the top 10 supercomputers. I think the only way to go forward is to create AI surrogate models from those. And of course, from the data we get from experiments. We need to have real-time interpolation of data during experiments, so real-time knowledge extraction in the end. And of course, inversion to reduce the on-the-fly data by orders of magnitude in the end. So this is a pretty clear workflow, and a lot of people are doing this, but I'm going a bit further because already bringing together all the building blocks. So for example, edge AI being very close to the detector in order to do a lot of reduction on data is not always implemented. It's very, very often implemented in prototypes already, but going from a full workflow, starting at the detector towards then later full storage and archiving of that data is still not implemented in total. So one of the critical things we shamelessly stole from particle physics is, of course, to create fully digital twins of our experiments for planning those experiments, for formulating hypotheses and showing that experiments are exactly feasible and giving this as an input for the automated facility. So in the end, we want to do it similar than in particle physics, to really have as closely resemblance between the experiments at, for example, photon facilities, as compared to what we can simulate in a simulated experiment. However, it is much more complicated than this, than in particle physics, because usually our systems change, the detector setups change very strongly, and also the communities using these apparatus are very diverse. So we have a much more fragmented space of solutions that we are facing towards this. We need scalable AI models to really go forward and do this on top 10 supercomputers. So you just saw the 20 petabytes per minute again, and the 27,000 GPUs in order to really bring this into an AI model that is really resembling the large-scale simulations you just saw. You have to make it really scalable. This is even possible for things like physics-informed neural networks and other architectures today to really go there. And we are currently in the phase of developing these and really applying these and combining this with streamed output into from simulation into large-scale AI models. Then you really have to make use of the inversion capabilities of modern neural networks. So what you have to look at is that you can really create synthetic data that resembles your experiment very well and connect it to a very realistic simulation or digital twin of your experiment. And by this, you can then invert from experimental data back to the most probable simulation parameters that can describe what you're seeing or tell you that you really have an outlier here and take further action on that one. So this really means that you have to put as much physics knowledge into the networks as possible usually. And of course, there are a lot of ways to do this. One is physics-informed neural networks for many of these simulations that drastically reduce the need for training data, and also give you high confidence on the numerical precision of your codes, especially if you put in further information like symmetries or other things of the system. And in the end, you have to do an approach that really starts from the very fundamental physics, like quantum physics of matter under extreme conditions, and then go forward to across multiple length and time scales to really give information on full material properties. So you're really combining very different simulation techniques, from quantum mechanical approaches to relativistic plasma simulations, and you're going across different scales. So for all of these scales, you have to have a common framework to connect those different information and give meaningful and reliable results in them. So this is one of the projects we're doing, is the MALA project together with Sandia Lab, trying to connect all of this different information on the different scales with AI to give you full multi-scale ab initio model of materials response under extreme conditions. And here are some of the recent results we got with this. So if you have ever been on an HPC system, especially if you've been for quite some time on IBM systems, DFT will be one of those simulations that took all your simulation time away from you, because it is always a very nice tool to fill up all the clusters. So density functional theory is one way to compute complex many-body quantum systems, and usually you end up with a few thousand atoms. But if you really accelerate this with AI surrogate models for certain atomistic properties of these DFT simulations, you can really scale this up by a factor of 100 to 1,000. And this is a real game changer. At the same time, you can really now do visualization at 20 petabytes per minute, and you can especially also stream this into AI models, so you really can interact with your simulation by now, look at it live at a supercomputer and stream it towards an AI surrogate model. And at the meantime, you can really also replace certain algorithms that are NP hard, for example, path integral Monte Carlo, by now AI models that run on your laptop and give you much better experimental results than previously possible. So this is really happening, this is going on. And this is combined with digital twins of full particle accelerators and light sources by now, that also help to optimize all components of these light sources in almost real time, understanding both the 6D phase space and the light generated by these XFELs. So here's one of those beamlines that is happening to be at HCDR and is driven by a compact plasma accelerator itself. So this is an XFEL driven by a small plasma accelerator that can still produce light in the EUV and hopefully soon X-ray regime. And we really bring forward these surrogate models connecting to different modalities of detectors. So not just diffraction imaging, but also density measures and so on. So we really bring in this information on the system for the different detectors, and we combine all of these, because usually with one detector alone, we cannot fully do the inversion on the right parameter set defining the system. So we usually have to really go for a multimodal setup and bring all the information from different detectors together in order to be as close as possible to the parameter set describing the experiment we are looking at, or as I said, understanding why it doesn't work, which is very often the case. So in the end, we also have to make the inversion algorithms better, not just by inverting models, but also in real time to just get better results. Here's, for example, one of these standard algorithms for phase retrieval. So getting the information that is usually missing in a scattering picture combined, compared to a neural network solution for that. And you really see that the standard algorithms are failing to reproduce what you see here as ground truth, while the neural network kernels have no problem in dealing with non-convex scattering problems by now. So this is a really nice development that we are seeing on many levels, improvement in terms not just in speed, but also really accuracy and better results. And in the end, you have to really combine this with workflows. So you really have to make sure that all these interconnects are going from the detector and from the intelligence at the detector towards larger workflows in the online data analytics center, combined with workflows in the HPC center, to really understand how data is transferred in an online manner and reduced as much as possible. But the main point is that if you do something like this, you have to take care of the quality and explainability and all these things of the AI model. So what we really have to develop is a full ML ops pipeline that allows you to not just create models, but also do the data versioning, take care of validation of your AI models. You have to optimize the training, and you have to really version your models. And you always have to also allow for human input that from experts that additionally evaluate those models in terms of performance and quality. And I think that's now state of the art. If you look at, for example, how much handiwork is still going on with solutions like GPT, where a lot of people are taking care of the quality of the outputs. This is really necessary to automate as much as possible the infrastructure for getting reliable and explainable AI models that also perform in a certain manner and in a certain time as you wish. For example, if you have a edge AI model that needs to get a task done in a certain amount of time, that's not and with a certain accuracy, that's not an easy task. That's usually not an easy task to do. And so you have to take care that all of this is well tested, and with every change and with every retraining, you are still allowing for to pass all the tests that you're imposing on such models. So I think this is becoming standard right now. I've been giving this talk for quite some time, and I see that this is finally catching up with at a lot of facilities, and I think it's also catching up at CERN. But many facilities face very, very specific problems in implementing this at different parts of the facilities. For example, for us, it's very complicated to get reliable and reproducible results from the systems that we are looking at, because they are highly nonlinear, and reproducibility of experiments is still not at the standard like at other experiments. So what you usually need to do is repeat these experiments very often. And we again hope that with AI automation of the experiments, this becomes not just easier and more optimized, but also we can really give feedback on how to optimize our measurement process and stop when we do not need further measurements, but also drive experiments towards optimum parameter search in performing the experiments. This will enhance both quality, but also time to solution of such experiments. In the end, there is a lot I cannot cover in half an hour, like the use of robotics, so in making the experiments more versatile, but also better. For example, it would be lovely if I could really turn this little target you just saw in the beginning with my hand, with some data glove, and with high precision, a robot would do the same with the target, and at the same time I could give some output, what would happen in a simulation, and would see what could be done in experiments. So this would be cool to have, and it could be directly interfaced to AR or VR capabilities, so I can directly see what's happening in experiments. But this is still further down the road and would allow a very different interaction facilities. And just because every talk today has to have some example of GPT usage, I guess, when you talk about AI, GPT-4 has just released a 32K tokens version. If you're not familiar what a token is, it basically is the atom of language understanding for large language models. And the more tokens you have, the more contexts you can have. So with few tokens, you can just look at one sentence. With more of these, you can actually look at full chapters or total books. And the more tokens you have, the more context you can get. For example, if you want to really understand a large scientific code, you want to load it fully into your model in order to understand it. And these are really game changers now. You can really put large contexts in there, and it's getting huge. At the same time, this is a very nice and cute thing called AutoJPT, which you can find on the net, which showcases actually autonomous task completion. So you can use the API, the OpenAI API, and connect GPT-4 to other tools. So whatever tool you have, you can connect it to that and let it also select new tools and autocomplete autonomously tasks. And this is a very different view of taking science. If I can, for example, tell my experiment in the end, rotate the target until you see this and this effect, and it for example, until you see the strongest occurrence of a certain plasma instability. This is an amazing interface to really describe very complex workflows that can then be automatically created while doing the experiment. And I think we haven't even started in understanding how this will transform in the end the use of facilities with AI. And with that, I'm finished. I thank you very much for your patience and interest in my talk, and I'm very open to hear questions and answer them. Thank you very much.
Thanks a lot, Michael. Thanks very much. Any questions to Michael?
So that was a lot of photon science. That's what I'm doing.
Attila.
Maybe just a bit of a question, because as you mentioned, much of what you were talking about are things that that are done relatively routinely in particle physics, mostly around detector simulation and just simulating what the experiments are doing. I got a bit confused at parts in the presentation on how AI models are meant to be trained in certain situations. At the same time, I was not entirely clear, even at certain times, exactly what is being simulated in various cases. So you showed some examples of their, let's say, the evolution of plasma was simulated. That I sort of understand. But then it comes to the very buzzword digital twin. I'm not sure what those simulations would be based on if there is no actual simulation to start from.
So I know that a simulation usually is used sometimes almost synonymously in particle physics with what you would call a digital twin. If you talk about detector simulation, it's actually a very convoluted simulation of different systems and of the system you're looking at. So in the fundamental process, usually using some form of Monte Carlo generator, and then the reaction of the detector itself. In other research areas like photon science, it becomes even a bit more complicated, because the systems we are studying, even at a single beamline, so where you have some different detectors with very different purposes, the systems you are looking at and the physical processes can change from day to day, because they want to look at similar structures, but at very different systems. So in the end, for each of these fundamental systems simulations, I have to create surrogate models. So it's not just plasma simulations. It can be a biological simulation, or it can be a certain material for energy storage. So this is the first problem that we are facing, that we have very different system simulation, and that also convey very different things on these systems. And we have to, from that, create the synthetic measurements from the different detectors. And at some facilities like synchrotrons, we can have 30 different end stations with very different X-ray beam properties and very different detector setups. And in principle, we have to connect all of these different simulations to those various end station capabilities and detector systems. So this is why this is a bit vague, because in the end, the variability and also the application areas explode compared to particle physics.
I guess my fundamental question is, in these cases, do you base do you train your models on data that you would have taken with these, or do you have some even more fundamental computer description of what you expect these things to do? Then you train your model on that, and then you run some large statistics with this help. This process is not entirely
okay. At best, both. Right now, the main high quality data in our case exactly comes from simulations, and usually from ab initio simulations based on the fundamental processes. This is why these simulations are so huge, because they really include the fundamental interactions that you know and that can reproduce almost everything you would expect to see in experiments. Although it always means that it's a limited view of reality, and that the dirty experiments we are doing are cannot always fully, for example, provide reproducible starting conditions for those simulations. We are now starting to also include in these simulations experimental results from previous experiments to enhance the quality and predictive capability of simulations, especially in areas where we know that our existing models are not good enough. So in the end, I think the simulations and the surrogate models we will be using in the future will include data both from simulation and experiments as well.
Okay, thanks.
Okay, thanks. Any more questions to Michael? I don't see any.
I think I'm preaching to the choir here. For photon science, this is still pretty much important.
Yeah, maybe for a bit of context, these days, well, at least whoever I talked to recently, whenever digital twins came up, we were scratching our heads a little bit as to what this would, or what this should mean for high energy physics.
Absolutely. I think high energy physics has for a long time been doing all the relevant things for their kind of models, but depending on to whom you talk to, for example, the Earth and the digital Earth community has a much different understanding of what a digital twin encompasses compared to particle physics, for example. But you have a head start of 30 years. Always remember.
Okay. Bon, I don't see any more questions.